Okay, so good evening everyone again to the third week of semiconductor microwave devices, and I'm Shahzan Bhatt, and I'm a PhD student at IIT Bombay in Applied Quantum Mechanics lab. So as per the protocol, we have to introduce ourselves every time we have this session, and this course is being offered on NPTEL by Professor Digvijoy who's a professor at SENSE Department of Nanotechnology and Electrical Engineering in Indian Institute of Science. So you might have seen the lectures previously, what professor has covered and what are the things he tries to finish in this particular week. So it was purely, I should say he tried to cover from the theoretical aspect what are these different devices. So that's what we will be covering today. So we will be covering this week three, which is some transfer electron devices, gun diodes, impact, avalanche diodes. So what are these, I should say, jargons which are used by the people maybe, but they are very complicated devices, much more complicated than the PN junction you might have studied in the device physics course. But again, if you know the device physics, if you know the PN junction, then only you can understand these devices. If you don't know PN junction, then you need to go back, revise those concepts, and then come back to these devices because these are a little more complicated than normal PN junction you might have studied in the previous lectures. Okay, so, what are we going to cover today? Maybe we will be covering a little bit of more physical aspect about these devices. The professor has already covered a lot of stuff in his lectures, but we will be kind of revising those concepts maybe, which will be used in the questions which are present in the assignment three of week three session. So some of the questions are definitely related to gun diodes. They are related to the working of the impact avalanche diode. So we will be seeing about also there is one more which is a tunnel diode. So those are all kind of I should say transfer electron devices which are used for high power and microwave applications. Now without wasting more time, we can actually get started. Let me just start with. Let's see what we have here. Just okay, maybe you might maybe we have a brief outline of this today's lecture will be first we will be trying to cover impact diodes. I think the first we will talk about a basic diode. What is the basic diode picture? Then we can move on to impact diodes. Then we can talk about maybe tunnel diodes. Then we can talk about what else? We can talk about gun diodes, and we will talk about its physics, operation, little bit of maybe maths, and some analysis, and then finally we will jump to the questions which are present at the end. So those questions are pretty basic. If you just understand what are the different operations or the what is the physics behind these devices, then you can just those questions are just cakewalk. You can just solve them in maybe 5 minutes or 3 minutes. So first of all, we will talk about the basic device physics. So in the first lecture, you might be remembering that we talked about a basic PN junction diode, a PN junction diode. And here we have a word junction. So what does this junction mean? This junction means it can be of two types. It's either a metallurgical junction or it's either a space charge region. What I mean to say is that let's say you have a P side, you have a P material, you have an N material. You combine those two materials. When you combine those two materials, that's not the way you combine, but just to make you realize how you can understand. When you combine those two materials, let's say you have a physical junction here, which is separating these two. This is something called as metallurgical junction. Metallurgical junction. So it's different from the I should say space charge junction. What you see, space charge junction is also here. So the space charge will be formed here. So you know that particular thing because you have positive ions and an extra electron here. You have a negative ion and a hole here. So these will electrons will try to go here. Holes will try to go here, and they will equilibrate. So under equilibrium So net electrons going here and net holes going to the other side will be equal, and you don't have any flow of the current in equilibrium when you don't apply any bias to the device. So how do you draw the band diagram of it? So the band diagram looks something like this, because there is a charge in the middle, which is the space charge region. So there will be bending near it because of the generation of the inbuilt field. So you have the electric field in this direction. This is the direction of the electric field. So whenever I write E with a sign of this on the top, this is electric field, because electric field is a vector. If I just write E, then this is energy, and energy is not a vector, it's a scalar. So remember that this sign I use mostly for writing the vector quantities. Okay, so this is the conduction band, and this is the valence band, and the Fermi level is exactly in the middle, exactly in the middle, and it's aligned. Fermi level is flat. That means at equilibrium there is the net motion of electrons from n side to p side, and of holes from p side to n side is equal. That means there is no net motion of the current. So if this is p side, this is n side, then at equilibrium there is no net current flow, because the current cannot itself flow in the device without the application of the external bias. Okay, now what happens? You have this particular region, which is this particular region. This is something called as depletion region, W depletion. That is the old depletion region you might be knowing about. So the similar concepts we talked about in the previous lecture, we talked about what happens if we have heterostructures. Heterostructures means those structures where the which have a different band gap, let's say. Here you see that we use a material with band gap Eg, we use a material with band gap Eg. So both of these materials have the same band gap, and as a result you have this type of a band diagram formed. Now what if you use a different type of band gaps on different type of materials with different band gaps on both of the sides? Then you saw that certain band diagram may look like something like this. That's not a way to draw it. So let's say if you have, let's say, AlGaN, aluminum gallium nitride, and you have gallium nitride, then you have a different phenomena altogether. The aluminum gallium nitride has a band gap of approximately 4 electron volt, and the gallium nitride has a band gap of approximately, let's say, 3.4 electron volt. Let's say if it is predominantly n-type and this is also n-type, then you know at equilibrium what is going to happen. And because these particular materials are something called as polar materials, silicon is not polar. Why are these polar? That we have covered in the previous lecture. There is a huge electronegativity difference between the nitrogen and the gallium. So there is slight negative here, slight negative, slight negative, slight negative, slight positive charges, as a result of which there is something called a spontaneous polarization developed at this end of this, so that the gallium on this end, this particular end, the gallium nitride on this particular end behaves like slightly positive, and on this end behaves like slightly negative because of the spontaneous polarization developed. So similarly is for the aluminum gallium nitride, but aluminum gallium nitride has also a component from piezo polarization. Piezo polarization. Why? Because if this is gallium nitride, if this is aluminum gallium nitride, if these are the atoms of gallium nitride and these are the atoms of aluminum gallium nitride, then you see that there is a lattice mismatch. If the lattice constant of this is A1, this is A2, then A1 is not equivalent to A2. As a result of this, the lattice of AlGaN has to either it has to stretch. Okay, that induces something called as piezo polarization in it. Piezo polarization. The charges redistribute because of the piezo effect. When you stretch it, it develops an electric field. That is the piezo effect. So as a result of it, there is a charge. There is some charge which is piezo charge generated at this end. There is negative piezo charge at this end. So altogether, all of these charges result in a band diagram which looks something like this. So they look something like this. Okay, this is LGAN, this is GAN. So what does this charge do? What does this particular piezo charge do? Because it creates an electric field in this direction. Okay, so there are certain states at the surface of LGAN, which are called as donor states. They are called donor states because these are energy states, surface states. Okay, that means if this is LGAN, this is LGAN, this is GAN, then there are certain states here on the surface of AlGaN which are donor states. They donate the electron, because there is negative Pz here plus Pz here, electric field is in this direction. The electrons come and settle at this particular layer between the GaN and LGaN. So that is this layer. These electrons come and go down. Basically, there has to be a bending here, which is because of the electric field. So there is a bending like this. So the electrons go down, they settle in this region, and you have something called as two-dimensional electron gas present here. And notice that these two materials here, they are not doped. You don't dope this particular thing, you don't dope this particular thing intentionally. Sometimes it may be done, but most of the times it's not done. It's already doped, or because when you fabricate these materials, let's say using something called as molecular beam epitaxy, maybe because of the impurities there, it may get the gallium nitride may get carbon doped, C doped, or it may get silicon doped. So because of that, there is some little bit of fluctuations in the energy levels also, but you don't need to consider that. So this is the concept which we have tried to cover in the previous lecture. Now, how is that going to how is that going to be useful in this particular lecture? So let's talk about if we talk about let's say first of all, impact device. What is an impact device? What is an impact device? So it is similar to that of a PN junction. The physics is almost, I shouldn't say similar. The band diagram and other things have the similar concept. They come from the electrostatics. So this device looks something like this. If you have let's say N plus region here, you have a P region here, you have an intrinsic region here, and you have a P plus region here. Okay. So why is this going to be useful, and why is this used? And this can also be a structure like this. If you invert all of these, if you have this P plus, you have this N, you have this intrinsic, and you have this N plus. This can also act like an impact diode. What is the difference between this and the brown one will be clear after in a while. So what happens is that because of there are two different materials, so there will be a depletion region formed. There will be depletion region formed here, maybe here, maybe here. We'll talk about how much is that depletion region, or whether that is appreciable or not. That's a different question. But whenever there is a junction, there will be depletion region. So between in this junction, in this particular region, the depletion region forms, but you know that because this is higher doped and this is lightly doped. So you know that the depletion region penetrates more towards the lightly doped region. Okay, so this will be entirely kind of in a depletion. It's not P, it won't be positive. So when the depletion region will form, this is P. So when the depletion region will form, maybe there will be slight depletion here, but this P will be entirely depleted because it's slightly doped. Okay, so this is intrinsic region, so there is no effect here, but the most of the depletion region is present in this region. So you see. So that happens similar in the what happens in the PN junction. If you dope one side higher, if you dope other side lower, the depletion region penetrates more towards the side which is lower, which is lightly doped. So that is covered in semiconductor fundamentals. And when you draw the charge profile, what you draw is you now have a delta charge here, which is a negative charge, and because of it there's an electric field present. Okay, you know that from the basic device physics course. Now, if you extrapolate these lines and if you draw, let's say, a profile, which profile I'm talking about, let's say an electric field profile, or if you draw a band diagram profile. So how it looks like, because of this electric field, because of the electric field, there will be built-in potential, and this marks as a bending in the band. That is from the basic p-n junction physics also what happens, because if you have a region like this, you have an electric field in this direction, then there is a built-in potential developed. That is the similar phenomenon. So if you draw the band diagram, it looks something like this. There's a steep increase in the potential, which is the electrostatic potential. Now this is the conduction band, and then there is a slight increase here. And similar happens to what happens to valence band. So if you draw the valence band like this, then there is slight increase. And if you draw the Fermi level at equilibrium, Fermi level will be flat throughout, but you have to make sure that this region remains N plus in the bulk, this remains P plus in the bulk, because these are two different regions. Okay. So how will you make the Fermi level? You will keep the Fermi level closer to this region because it's N plus. Then when then here it's P region, then it will be slightly towards the P, and then it will be in the almost in the middle. So it's not exactly to the scale, but Fermi level is flat throughout. This particular thing should be flat throughout, but it should not lose the property. That means this particular thing should be intrinsic. This particular thing should be this particular thing should be N plus, and this particular thing should be P plus. It should always remain the in the natural state at equilibrium. At equilibrium. Okay. So you see the Fermi level here is closer to valence band, that means it's P plus. Here almost the Fermi level is in this region, the Fermi level is middle, that means it's it's an intrinsic region. And here, if you have a like bending like this, then this particular thing should be closer, it's closer to the valence band, that means it's P plus. And in this region is closer to the conduction band, that means it's N plus. Now you have this particular conduction band profile, you have this particular band diagram. Now what is going to happen? So what is going to happen is that now, if you have, let's say, an electron at this particular position, the electron is going to drift down because it's like a downhill motion for the electron. Similarly, if you have a holes at this particular position, they are going to drift uphill because whenever you draw the energy band diagram, this x is E of x, which is the energy, electrostatic potential energy. This is for electrons. Okay, so that's why in the up direction, the electrostatic potential energy of electrons increase and the holes decrease. Okay, so that's why holes are moving in this direction, the electrons are moving in this direction. They want to go to the lower electrostatic potential energy of their respective ends. Electron wants to go to the lower potential energy, hole wants to go to the lower potential energy. That's why they're moving because of the drift. Now, now that creates something like a, I should say, oh God. Just give me a moment. I'll be back. I have an important call to receive. Just give me a moment. Where is Hello, हेलो. 2 मिनट दीजिए, मैं आता हूँ. Yeah, just give me a moment. I'll be back in just 2 minutes. Just give me a moment. Yeah, sorry for the interruption. Let's get back. Okay, so where are we? Okay, just turn this off. Okay, so this is the band diagram of this particular structure. Now, what happens is that due to huge bending or a huge electric field at this particular region in this particular region, so there is something called as avalanche effect that happens. Avalanche effect, and what it means is that if you have a, let's say, a bending like this, if you have a bending like this, then you know that electrons can go down the hill. Okay, when electrons go down the hill, they lose their energy. They have the excess kinetic energy. The first of all, let me tell you what is kinetic energy for the electron and what is potential energy for the electron. If you have a system like this, if you have electron exactly at conduction band edge, then it's having only potential energy. It's not having kinetic energy. Okay, because that is the potential energy profile you draw. That is that means if it is exactly at the conduction band edge, it's having potential energy. And now if the electron is somewhere like in the above states, above the conduction band, this particular excess energy is the kinetic energy of the electron. Then the electron can transition from higher state to lower state and reach here, and it now has converted its kinetic energy and now it has only potential energy. Okay, these are different energy levels present here. Okay, now that is the case. What happens when an electron transitions, when an electron goes down the hill, it's not as if electron is going like a ball. It's not as a ball. It does not roll down like a ball. That's not how the electron behaves, because electron is present in certain energy levels. Okay, so there are certain energy levels here. There are energy levels throughout the conduction band. Okay, an electron is present here. What it does is that it goes little bit, moves forward, then it goes down, moves forward in another energy level, then goes down, moves forward, then this particular thing happens. This is the exact thing how the electron moves down the hill. That is what we mean when electron moves down the hill. It's not like a classical ball moving. Okay, now what happens during this process is that once the electron goes down the hill, it increases its the kinetic energy increases. I should say it becomes more and more energetic. Why it becomes more and more energetic? Because it attains up to a certain particular threshold velocity called as saturation velocity. It keeps on attaining that particular energy, because you know that kinetic energy is half of mv square. Okay, so it goes down the hill, and in that particular process, because when going down the hill, it's very energetic. Okay, so when it goes down the hill, if there is some other atom present at that particular position, which is there definitely. So there are 10 to the power maybe 20 per cubic centimeter of atoms present. So it hits another atom. So if this is an atom, electron comes in. If this is having another set of electrons, then this electron hits the particular, it doesn't hit physically. It's a different quantum mechanical process. So it perturbs the atom, it disturbs the atom, it knocks out another electron. So that particular electron again goes down the hill. This is the scenario I'm telling what is happening here. This is happening here at this particular position. Okay, that's I'm zooming. So these particular electrons go down, knock another electrons, and a cascade process happens. That means if there is one electron, it gives rise to two other electrons. These give rise to four electrons. So this is a chain reaction happening, just like a fission process. When you split the atom, that's the similar process what happens in a fission, nuclear fission. That's what the atomic bomb is based on. So a similar process happens here. That's why it's called as avalanche. In the avalanche, when the snow falls down the mountain, snow when it rolls down, it starts to accumulate and it becomes huge and becomes bigger and bigger. That's why it's called as avalanche. So as the electrons go down the hill, it starts to accumulate more and more electrons. And by the end of this particular, you have such a huge concentration of electrons that it causes a huge surge in the current. Okay, that's why you might have seen in the reverse bias case of a normal PN diode, you have the forward characteristic like this, where this is something called as cut-in voltage. Let's call it V cut-in. And you have in the reverse bias, you have a very small current. Okay, reverse bias, reverse saturation current, which is let's say I naught. But if you cross some particular value, which is V zener, or let's call it some V dash. If you cross that particular V dash voltage, then current abruptly shoots up. It's because of this particular process. the in the reverse bias, the diode starts to break down. Normal PN diode I'm talking about, okay? Because in the reverse bias, what happens is that there is huge band bending, okay? Now there are other processes that happen in the diode, why the breakdown happens, but this particular avalanche breakdown is one of those reasons. The other reason is tunneling, which I will discuss in tunnel diode. So avalanche breakdown means these electrons go down the hill, and the hill is so steep that as it goes down the hill, it keeps on generating more and more and more electrons. Now, how do you use this particular process here for your better, for your advantage? In the PN junction here, you have seen that this particular process where the current increases, there's a surge in the current. This particular process is not advantageous. Okay. But in certain devices like Zener diode, this has certain advantage where you can maintain a constant voltage. Okay. But definitely current is huge, but you can maintain a constant voltage. But how are we going to make it good for us? That's what this particular impact diode does. So for the avalanche effect to cause the breakdown, it should have certain minimum length of this particular region where the avalanche is happening. So there is a certain length threshold. So there is a certain length of this particular P region. Let's say we are talking about here this P region. So there is certain length of this P region over which if you let's say there is certain threshold length. If that length crosses this threshold, then there will be breakdown due to avalanche. Okay. And if this length is less than threshold length, then there will be no breakdown. And there will be still more electrons, but not enough to cause the breakdown. Okay. Not enough to completely break down the device. That is the notion of this particular device. Why that is the reason why this particular region is kept narrow here, and why other regions are kept, I should say, longer than this particular P region, because you don't want you don't want what is called as avalanche breakdown to damage your device and cause a catastrophic failure. Okay, now that is the particular scenario in this system, and even in PN diode, even if you can control this particular region, you can even make that particular process to happen. You can use it for your own advantage, and even in certain Zener diodes, this process is still used. Zener diode works in the reverse bias system, and you use that as a voltage regulator in order to control the voltage in your circuit. That uses a similar phenomena. So if you talk about a Zener, that's something called a Zener breakdown also. And this process, which is used in the Zener, that uses avalanche breakdown, and that also uses something called as impact ionization. The impact ionization is basically a part of avalanche breakdown. Impact ionization means one electron hits another, it ionizes that atom, creates electron that ionizes another atom. That's it. Okay. Another process here that happens that causes this sudden surge is tunneling, that we will discuss in tunnel diode. What is tunneling? That is also a reason, one more reason why there is a breakdown, why there is a huge surge in the current and reverse bias of a normal PN diode. Now this is the impact diode. So this is the working of the impact diode. Now because of this huge surge in the electrons, there is I should say, a pulse of current created because of this huge surge. That pulse of current, which is because of the electrons, because you know that current is N, Q, mu, E. Okay, so it depends upon the number of electrons. This is basically the current, what should I say, current density. So it depends upon the number of electrons. It depends upon the charge is constant. It depends upon mobility. It depends upon the electric field. So if you have a huge density of electrons, let's say 10 to the power 20 per centimeter cube of electrons, compared to let's say 10 to the power 16 per centimeter cube of electrons, so this is N1, this is N2. Then definitely N1 is greater than N2, then I1 will be greater than I2. There will be huge surge in the current. Okay. So that is the notion of this particular device. Now what happens? Let me see, how are we doing here? Okay. Okay. Yeah. So now what happens is that this particular pulse of current, now the rest of the working is same. Now this particular pulse of current travels through this device, through the region of intrinsic region. If this is the If this is, let's say, N plus region, this is P, this is intrinsic region, and this is again this is P plus region. Then when you have this particular pulse of current produced, pulse of electrons produced, then you bias it. Particularly you DC bias this particular device, and that's why this particular device is mostly used to convert the DC signals to the RF signal or oscillating signals. And it has mostly the functionality of producing those oscillatory signals from the DC. That means if you apply certain DC bias in this particular region, then that is going to create a no, you basically produce, you give it a bias like this, then this particular pulse is going to propagate in this direction. Okay, because it's negative in this end. These are negative pulses, negative electrons, then they will be moving towards this end. Or in the on, I should say, in other words, if this is the band diagram of this, if this is the band diagram of this, if the electron is going this direction, the holes are actually going this direction. That's why holes are moving in this direction. And you might have maybe seen in the lecture that this is mostly a hole dominated device. Hole dominated device. Why it is hole dominated device? Because it is this region which determines what type of device is it, whether it's a hole or an electron. But to me, it's one and the same thing, because if an if a hole is moving in this direction, that means an electron is moving in this direction. Only that can happen, because they are kind of uh, I should say antiparticles to each other, electrons and holes. Okay. I shouldn't say that because you guys are not particle physicists, so that is the language particle physicists mostly use. Okay, but just let's omit that. So the holes are moving in this direction. Now the length of this particular region, let's call it L, that determines something called as transit time. Transit time is how much time these holes will now take to reach the other end of this particular device, reach this particular end, which is the P plus end. Okay. Now that is the similar procedure. You have a because you have now huge number of electrons here. Similarly, you have huge number of holes here because of this avalanche effect. Okay, because once the electron knocks out other electrons, it leaves certain empty states, empty orbitals, or empty energy levels. Holes are basically those empty states moving, or in other words, electrons moving from right to left. So that is the particular thing. Now this particular pulse travels in this direction with a time, certain time called as transit time, and that particular transit time is basically some tau. Let's call it tau tr. It's basically the distance divided by the velocity. Now, which velocity? It's the drift velocity, but it's mostly the saturation velocity, because the holes or the carriers, let me call it carriers, whether it's holes or electron, they attain a particular saturation velocity under the application of electric field. If this is V, this is electric field, then you keep on increasing, then you attain something called as, I draw it in the opposite direction. Let me draw it this way. If this is E, this is velocity, the carriers will attain a something called as saturation velocity. It's just like the saturation velocity is just like if you have the, if you have, what should I call it? If you have raindrops falling from the sky, then they attain something called as terminal velocity, because of the drag and other things from the air. The a rain droplet which is coming from the clouds, it cannot start increasing its velocity indefinitely till the ground point, otherwise it will attain a very huge velocity, right? But why does a rain droplet fall out with a constant velocity? That is the concept of terminal velocity, because there is a drag, and the upward forces and the downward forces balance. They can, I should say, equally balance each other so that it attains a constant velocity. That's why raindrops or even the hailstorm, wherever the hails fall, they fall with a constant that velocity. If that wasn't the case, those raindrops will hit you like a bullet, because it would have increased with the velocity as it travels to the cloud towards the ground, but they come down with a certain constant velocity, which is the terminal velocity concept. Okay, maybe if you are interested, you might look for it. But this is just maybe 11th class physics. That is the concept of saturation velocity. Velocity, once the velocity of the electrons increases, then it attains a particular saturation velocity. And why does it attain so? Because there is also drag inside the semiconductors, inside the solid state device. What causes that drag? There are certain resistive forces. Drag is the resistive force, which comes because of impurities, scattering, and other things. Let's say there are atoms, there are electrons moving here and there. Once it gains certain particular velocity, those scatterings start to come into process. Okay, that's why you might have seen that the mobility does not keep on increasing with temperature. The mobility reaches the maximum value at at some particular temperature, then it again drops. That is the reason. That is the scattering again. Scattering process happen. So there are many, I should say, n number of processes that happen. So that is the pure physics part of it. Now, those that is the particular velocity we use here, something called as saturation velocity. We sat, okay, attained at certain particular electric field. This called as some, let's call it E critical field or E saturation, whatever you call it. The name doesn't matter. You should understand the concept. Okay, now that is the overall, I should say, working, how this particular thing behaves. That means you have, let's say, you have a current pulse, you have current pulses, and the fascinating thing about these pulses are that they are pi out of phase with respect to the voltage, pi out of phase with respect to the voltage. Okay, let's say if this is some voltage signal, then these particular current pulses come at certain, I should say, angles. What should I call? And not angles, at certain delays, which is encompassed in the phase of this. So if this is pi by 2, if this is pi, then these pulses are out of phase by pi with respect to the voltage curve. Okay, so that out of phase nature gives rise to this particular oscillatory behavior. And and it's always, I should say, how should I say it? Let me call it, if this is some black box device, and if you are applying some DC, you are getting some high frequency signal out. So how is that particular thing happening? It cannot happen by its own that a single DC signal is getting converted to a microwave signal. Okay, it is the inherent noise which is present in the system that gets, what should we call, that gets amplified and causes these oscillations. Because a DC signal is just like a source of supply, it's just like a source of power which disturbs the system. The inherent noise present in the system, it gets amplified to the certain microwave signals. And how, why is that in microwave range? That's a different question, because we are tuning it to a particular microwave range. And one important thing maybe, wherever you study the oscillators in the electronics, in the electronic devices, they are all creating oscillations because of the noise present in that particular system. A small noise is always random. Noise doesn't have any particular frequency or oscillation, or just like if the microwave created at the output is like this, then the initial noise which might have created it might have looked like something like this, not a particular waveform. It's a random waveform. It's a random. Okay, it gets converted to microwave. That is the inherent process that is happening, and you are supplying the energy which is the DC bias, DC energy. Okay, that's why there is a whole, I should say, subject devoted to it, something called as random processes, random variables, and stochastic processes. Stochastic process, it's a I think it's a course in electronics and communication, because I have done it in my bachelor's. So the random process and stochastic, so random variables and stochastic processes, actually it deals with what these random processes happen inside, let's say, device. Or this is mostly a mathematical course where you can study about what these noise fluctuations are, whether they are having any pattern or not, how you can convert those pattern into something which is oscillatory. Okay, you study these processes in that particular course. Okay, but now the concept here is that what is going to happen. Let me let me see first, where is this particular thing. Okay, so we've covered this thing. Are we on time? Yeah. Okay. Okay. Hmm. All right. I think this thing has been covered by Professor. Okay, that is the thing. Okay, now let's see what else we have. Maybe some maths we will discuss. whether we have, yeah, this thing has been done. I think most of the things have been covered by professor, but I will mostly deal with the things which maybe professor has not explained in the lecture. Okay. So yeah, maybe this thing is better to discuss. So once this particular process happens, once the, let me not draw the band diagram like this. Let me draw it like this. Once this particular pulse, which is the pulse getting going into the intrinsic region, once that particular thing starts to move towards the intrinsic region, so it gives rise to something called as injection current. Injection current, and let's denote it some I of t, which is some charge per unit time. And time again you can write in terms of the which is the transit time basically. So the charge divided by what is the transit time? The L over V sat. So you can write it as Q V sat divided by L. A simple relation. It's not a, should say, not a deep mathematical thing. So this is the injection current which will be flowing through this particular thing. Now, one of the important things is that you need something called as resonator circuit here, resonator cavity or a circuit here in order to sustain those oscillations. Why is it necessary? What is this concept of resonator circuit? If you have a single impact diode like this, and if you give it some DC bias, you expect you get a microwave out. No, that's not what happens. The microwaves will get out, but they will soon die out. Okay, they won't be able to sustain those oscillations. It will be somewhat like a decaying sinusoidal function, maybe a decaying sinusoid. But you want something like this, which is present till minus infinity to plus infinity in the time. Okay, something like which is always fluctuating, always oscillating. That is what you want from the device. You don't want a decaying oscillatory signal. In order to do this, that's why there's a need for resonator circuit, something called as resonator circuit, or let's call it as cavity, or certain other cases there are certain waveguide resonators used. So let me briefly tell you about what happens. Let me give you an analogy. Maybe that quite clear what this concept basically is. So you take this impact device and you connect it with some maybe other LRC circuit, maybe LCR circuit. What happens is that whatever the oscillations are created initially, they pass through this LCR circuit, and there's a feedback loop which keeps on going so that they can maintain those oscillations, particular oscillations at that particular frequency. Okay, now this particular LCR circuit has certain tuning frequency. You know it from the basic electrical tuning frequency, something called as resonance frequency. Resonance frequency. And that is the characteristic of an LCR circuit. The resonance frequency, what it depends upon inductance, capacitance, resistance. You can tune it as per the values of the inductance, capacitance, and the resistance. I think it is approximately 1 over under root LC for a LC circuit. Or you can write 1 over 2 pi under root LC. That is the resonance frequency of an LCR circuit. So you need to match that resonance frequency exactly when you place that impact diode in this particular resonant cavity. And if you know that omega, you can write it as 2 pi f. So you can write this as maybe you can write this. Let me try to remove this. Why is this not responding? So if you have this particular system connected with the impact diode connected with the resonant circuit, then you can have the relation that omega times transit time should be equivalent to pi. That means after every you want a pi phase shift in your particular signal in the current. So that is going to give you the condition that the frequency is basically the saturation velocity times twice the length of the what's called as intrinsic region. Okay, so what is this particular frequency? It is the frequency for negative resistance. We have not discussed about the negative resistance, but is the frequency for the LCR circuit to sustain. That means it should resonate at that particular frequency. We have to tune those elements of the inductance, capacitances, and the resistance in such a way that it should match this particular frequency. That is the entire concept of how it resonates inside this particular circuit. And resonance is quite a, I should say, it's quite a phenomena which we have been studying from class 11th maybe. That is the similar phenomena which happens maybe if I can give you an analogy. If you have if you have a laser, little bit of deviation from the topic, but maybe this might give you an idea what resonance basically is. If you have a laser The laser has something called as active medium. Active medium is the material which emits light, which emits light. Let's say, for example, you have, let me take which example? Yeah, let me take something called a neodymium. Nd is an element. Let me call it neodymium. It's an element. We have neodymium atoms. If you just pump it electrically, if you just give it electrical energy, you will see that it emits photons. Okay, and those photons have certain phase relationship between them. Let's not go into that. They are something called as coherent. That means if this is one photon, if this is the one electromagnetic wave, then the other electromagnetic wave exactly looks like this. There is a certain phase relationship between those electromagnetic waves. So that's how you basically have the lasing action. But a simple neodymium element does not itself give a laser out, because soon what happens is that these particular oscillations they fade out. They cannot be kind of used as a particular laser. Okay, so that's why what you do is that you take a neodymium atom, you place it inside a cavity. Cavity is like this is a mirror. This is a mirror. It's not a physical mirror. This is done at nanofabrication level. But consider these as mirrors. These are exactly mirrors. They reflect the light back and forth. Okay. So what happens now if you electrically excite it, you give the electrical energy, something called as pump. This neodymium atom emits light, a photon, that hits the mirror, goes back and forth in this cavity. That again hits this neodymium atom, creates more population, creates more photons. And this keeps on going on, and it keeps on going on till the I should say a significant photon number is reached inside the cavity. Okay. Once that particular photon number is reached, then this particular mirror, which I have shown on the right side, this particular mirror, it transmits those photons. How does it transmit? That's a different question. You won't get that right here. This mirror transmits those photons at when it reaches certain threshold, and you have a huge strong burst of light coming out. That is the concept of cavity. And this is something called a resonator cavity. Resonator cavity. Why resonator cavity? Because the light resonates in it. The particular distance between the two mirrors, let's call it d, it basically signifies that what should be the resonance, what frequencies of the light to select which can go out. It is the same concept which happens in LCR circuit. If you can just relate it, because this particular thing is also a resonator, LCR circuit is also a resonator. That is a what is a resonator? It's a frequency selective network. It selects one certain frequencies, and it then creates the back and forth, oscillates them, creates back and forth oscillations, amplifies it, and then takes it out of the resonator cavity. That's what happens in the laser. That's how you get the laser action. That is a similar phenomena what happens in the LCR circuit. If you have certain frequency, and if it matches the LCR oscillation frequency of the circuit, then that particular frequency is going to cause the resonance, something called as when the incoming frequency matches with the natural frequency of the system, you have a huge resonant peak. You have the peak in the amplitude of the signal. So that is the entire process that happens inside this particular device. Now they are the laser and this particular device, they are two different phenomena, but the concept is pretty similar. The maths is pretty similar. The concept is pretty similar. And even in, I should say, normal class 12th example, a class 11th example, you might remember a string which is tied at two ends. This is a string tied to two of these ends. And if this is the length of the string, then this string can vibrate at only particular frequencies, which are its natural frequencies. Okay. And if you match the external vibration to this natural frequency, you have caused the resonance and you get a huge amplitude of those strings. Okay, that is I think F equals to V over twice L is the natural frequency of this particular system. And you can actually compute it. How you can compute it? Let's say let's say this is L and let's say you have something inside, and if it hits this particular end, then it goes back and forth. Then in order to traverse this particular region, it has to cover, let's say the ball hits this region, then has to go, it has to hit this region. That means it has to traverse this particular length twice. Okay, then the time required to cover this entire region will be something, it's maybe it's velocity. No, not the velocity. Twice the length times the velocity. Okay, that would be the time which this particular ball will uh, need to cover this particular entirely in a full cycle motion. Okay, and you can change it to frequency. You can write frequency equals to velocity times 2 times the L. Velocity times the velocity times divided by twice L. That is the string tied. That is the simple ball. That is the similar thing what happens in a string. If you have a string tied at both ends, this is just like it can only have certain frequencies, allowed frequencies. For n equals to 1, it can oscillate like this. For n equals to 2, it can oscillate like this. For n equals to 3, it can oscillate like this. What is n? Those are different modes of the frequencies. Okay, this is like lambda, lambda by 2, lambda, 3 lambda by 2. Okay, the black one is the lambda, the red one is lambda, the black one is lambda by 2, the red one is lambda, the green one is 3 lambda by 2, so on and so forth. So there are only particular frequencies that can basically sustain inside the system. Okay, it's a very vast topic. The resonance is basically a very vast topic, and it happens at all of the systems, whether it's a mechanical, classical system. This is a classical system. Here it's also a little bit of classical system, but somewhat quantum is involved. But this particular resonance, it's you might have seen a similar phenomena when you have a confined structure. When you have a quantum well, which I talked about in the previous topic, previous lecture, if you have a quantum well and if you solve Schrodinger equation for this particular well, you have discretized energy levels. You have discretized energy levels. This is E1, E2, E3. And when you see the wave function of those modes, they also look like this. This is the first wave function. This is the second wave function. This is the third wave function. You see the similarity between these two? Otherwise, this is a quantum system and this is a classical system. But there is a similarity that only few wavelengths or the frequencies are supported. Okay, not all the frequencies are supported. Why? Because here only you have discretized energies. Discretized energies means discretized frequencies because E equals to H times frequency. Let me call it F. This is the Planck's law. E is H times frequency. So if you have the discretized energy, you have the discretized frequency. That is the same concept here. You have the discretized allowed frequencies or wavelengths or energies, whatever you call it. So it's always the game of energy, frequency, wavelength. If you have understood these three things, you have mastered the entire, I should say, electromagnetism and electrical engineering. That's it. Okay, too deep of a philosophical thing. Let me see what else we need to cover. Yeah, now important thing. Now, if we talk about now, we were talking about impaired diode connected with the resonator circuit. Now, what is the maximum power we can get out from this device? If you have an impaired device, there has to be some maximum power which it can give us particularly. That is the limitation of the entire, I should say, all of the devices. It will give you only a certain maximum peak power. And how you compute it? You can compute the maximum power. You know that power is some maximum voltage times the maximum current. But but you remember that these two are out of phase by pi. Okay. And what you can do is that using maybe certain tricks, maybe professor has discussed that in his class. You can write maybe the Vmax. Let me see what he has done. You can write Vmax as electric field, maximum electric field times the length of the region, and you can write current as current density times the area, because current density is current per unit area. Okay, and voltage is as you have written. Now you can write current density in terms of sigma times the maximum electric field, because the microscopic Ohm's law, from the microscopic Ohm's law, you have the current density equals to conductivity times the electric field. Okay, that is what I have written here times the area. and you have E max times L, which is the length of the intrinsic region. And now you have this conductivity can be basically written as not the conductivity. There is something called as relaxation time, which is basically conductivity times the permittivity of the medium. So what this relaxation time is basically is it's something called as Maxwell relaxation time. Maxwell relaxation time. And it appears in the Maxwell equation. Maybe you might not have heard about it, but it is the relaxation time with which whenever you have created a population of let's say let's say this is let's say these are there are electrons, there are holes, electrons and holes. No, let me not show it like this. Let me show it. If you have if you have conduction band, you have valence band, and if you irradiate it with light, what does light do? It creates electron hole pair population. Electron hole pair population, just like this. It's now a non-equilibrium situation because you have disturbed the system entirely. Now the time with which these particular charges respond as well as relax, that is something called as Maxwell or dielectric relaxation time. Particularly, it's mostly applicable for the case of, let's say, dielectrics. If you have a dielectric means let's say you have a let's say you have a certain material where there are positive ions and negative ions. So if you hit it with light, those charges are going to respond, and they are going to respond slower than that of electrons and the holes because these are immobile, these are heavy, electrons and holes are free, they are light, they have lower effective mass. These are ions, these are literally the atoms. Okay, now the time with which they respond as well as relax, that is basically covered in this particular factor, something called as Maxwell relaxation time. It comes from the Maxwell's equation. Maybe you can look it up. These directly come from the Maxwell's equation. It is basically given by conductivity divided by the permittivity of the medium. Permittivity of the medium. So you can tune the permittivity of a medium in order for the relaxation time to maybe change. So if you want such a certain mediums to respond fast, you can tune the permittivity of it. If you want certain mediums to respond slow, accordingly you can tune the permittivity of the medium. It's a very great concept, and it's mostly used in, I think it's maybe you might have seen it in MOS capacitor. In the MOS capacitor, this dielectric relaxation time is very useful in I should say inversion regime and beyond inversion regime. That's a different concept. Okay, let's leave that here. So this particular thing can be replaced by sigma can be replaced by tau relaxation times the epsilon. Uh, is it ulta? Is it ulta? Whether I've rated this correctly, let me check the units. I don't know. I'm not sure. Tau is time, so it should have units of second. So conductivity is nq times mu. Epsilon is farad per meter square. So this is n is number, so it's per centimeter cube. Coulomb centimeter square per volt second. This is farad per meter square. Capacitance you can write. Let me drop this. Q equals to CV, so you can write C equals to Q by V. So this is Coulomb by volt. This is this and this will go. This is Coulomb centimeter volt second. This is Coulomb per volt. Coulomb goes. Volt goes 1 over centimeter second. I think I've done a mistake here. Maybe what is exactly? I think yeah. This is ulta. Yes, the direct relaxation time is ulta. The relaxation time is epsilon divided by sigma, not the sigma divided by epsilon. That's why units were not satisfying. The unit should be second because it's time. Okay, yeah. So now you can again to tune the permittivity. It's a direct relation with the permittivity. Yeah, I made a mistake here. So the relaxation time is epsilon divided by the conductivity. So now you can replace the conductivity here and you can write epsilon divided by the relaxation time times the E max into the area, and you have the E max times the length of this particular device. Now, whether I have written this correctly? Yes, I believe so. Yeah. So now let's dive into the direct relation. So maximum power which can be which is this device can output can directly be written as E max square times the epsilon naught, epsilon s, saturation velocity times the area of this particular device. Okay, yeah, this is done. Yeah, this is good. So that is the particular maximum power which can be obtained from this device. Note that it depends upon maximum electric field which can be sustained. Now, what does this depend upon? It depends upon the band gap of the material. How much electric field can be sustained by a material without breaking down. Just like for a just like for all of the dielectric semiconductors, there is a maximum electric field. If you give that particular electric field something called as critical field, the material will start to break down. Okay, and that is particularly a property of band gap. If you have a higher band gap material, it will sustain more electric field. You can give a more higher electric field to it compared to that of a lower band gap material. So that's why higher band gap materials like gallium nitride and maybe gallium phosphide and other materials, aluminum gallium nitride, they are pretty much useful for such applications where they can sustain higher critical electric field, higher maximum electric field. So that's why for high power applications they are mostly used. Okay. And now what else you have here is that you can play with these permittivities in order to get maximum power out from the device. Saturation velocity is particularly mostly it attains the constant, but you can tune it maybe with the help of the mobility. Uh, and area is definitely you can tune the area of this particular device in order to get the maximum power out. Mostly that's not a concern. Mostly the material properties are changed by changing the material itself, by changing the band gap when you do it, you change the epsilon s also. So you have to accordingly see what is the maximum power you can get out from the device. Now this particular relation can also be modified, and you can write this particular relation as P max will be equivalent to E max square V sat square divided by 4 pi square xc times frequency square. Where does this relation come from? Basically, it comes if you have to use, let's say, certain something called as the impedance is R plus J XC. This is the impedance, which is the resistance. This is the reactance, which is the imaginary part of the impedance. And this particular imaginary part creates losses in the system. Definitely, apart from the resistance also creates losses in the system. This particular this is a particular impedance, and you can write it's not xc, let's write it x. You can then x, the reactance can be written in terms of the inductive reactance and the capacitive reactance, which will be the inductive reactance is the let me drop this let me write this. You can write the capacitive reactance as 1 by j omega c, and you can write inductive reactance as j omega l. Okay, these are just from your basic electrical concepts. And now using those relations basically in these particular equations, you can basically convert it into this particular equation. It's a very straightforward mathematical analysis. You have to use the capacitance equals to epsilon naught A divided by D. Then you have to convert it back and forth. Maybe professor might have done it in the class. So that's not the point of this session. The point is that we need to understand what is happening with this equation and what is this equation is telling us. I think we are running short of time. We need to speed up maybe for the other devices to learn. So this particular P max times the frequency square is given by something on the right hand side. Something on the right hand side. Let's call it A. And this particular A is E max square velocity, saturation velocity divided by 4 pi square, the capacitive reactance. Okay. Now this is a figure of merit of these devices. It's a particular important quantity where people mostly draw the P max here on the y-axis and they draw the frequency on this particular axis. And what people see is that it follows something like this 1 over f square. Okay, because the P max is varying inversely as f square. Okay, so this is the particular curve they obtain. That means at very higher frequency you get a smaller maximum power output from these devices. At lower frequencies, you get a higher power output from these devices. It has certain other reasons why that particular thing happens. Because at higher frequencies, other capacitive actions come into picture. Maybe if you see from this relation, if you have omega tending to infinity, xc tends to nearly maybe zero. But if you have omega tending to infinity, XL tends to infinity. So you have different variations of the capacitive and inductive reactances inside the system. So at particularly at higher frequencies, those capacitances come into picture, and you get you get higher capacitance values. And what does those capacitance values do? They create more delays and more phase shifts in this, because capacitance is like a storing of charge. So it's like charge storage element. Okay, and it can occur anywhere inside the device. It's not just like you have a parallel plate capacitor. If you have a certain charge separation, separated by certain thing, maybe a dielectric or some ions or something, it can have a capacitive action that actually stores charges. And this storing of charge creates delays in the system. Okay, so that's why it lags the system, creates phase differences in the system, which is not desirable. So the maximum power output reduces. Now this is the electronic, because of the electronic reason, electronic contribution. This all we have done analysis till now is because of the electrons are moving, just only the electrons or the holes, whatever you call it, just because of the carriers. I should call it carriers. Now there is one more contribution to it. That is basically the thermal contribution. Thermal contribution. What is thermal contribution? The thermal contribution says is that once you are operating this device, there is a generation of the heat. Now that heat needs to be extracted. Otherwise, it's not definitely going to cause a failure inside the device. Why? Because heat is a form of energy. It's like kT. Once you heat the system, you increase the temperature. You increase the temperature, you increase the temperature of the electrons or the electrons' energy. They go on increasing, and you have the failure of the device. You have the surge, current surges, and other things. So when you do the calculation, you can compute something called as what is this thing? Yeah, you can compute something called as thermal resistance. So thermal resistance is just like an electrical resistance, except that it is the resistance faced by the heat in moving through the system. And the heat is mostly dissipated via something called as phonons in the system. Okay. If it's a dielectric, I should not confuse it with dielectric. If it's a semiconductor, or rather I should say if it is non-metallic. If it's non-metallic system, then heat is mostly conducted by these phonons, which are lattice vibrations. And if it's metallic system, then mostly the electrons itself participate in the conduction of the heat. Okay, that's a very great concept. Maybe you might have somewhere studied about it. Okay, now what happens is that there is this thermal resistance, and this thermal resistance is this, let's call it RT. This thermal resistance is some temperature difference divided by what is this? Some temperature difference divided by the dissipated power. Or you can, in other words, write dissipated power as temperature difference divided by the thermal resistance. If you have this impaired diode, this is the impaired device, you connect it with certain heat sink in order to take out that temperature. So, and if the temperature of the this particular device is T1 and this is T2, then delta T is basically T2 minus T1. What is the temperature difference between the heat sink at this particular device? And what you get from this is another a similar relation, a relation between power dissipation times the frequency. You get that to be equivalent to thermal conductivity, the temperature difference divided by epsilon naught epsilon s. How this relation comes, it's not a maybe not a concern right now. It has a simple mathematical derivation. Maybe professor has discussed in the class. So the important thing is that this particular factor depends upon the thermal conductivity, it depends upon the temperature difference, it depends upon the permittivities of those mediums. And now you have another curve of the power dissipated, of the dissipation power versus the frequency. It follows like maybe somewhat like this, which is the 1 by f relation. And if you know from this particular curve, you have the 1 by f square relation, which was the maximum power which can be obtained from the system, and it followed something like this, which is 1 by f square. Okay, now these two curves intersect at this particular point. This particular frequency is called as corner frequency. Corner frequency. Okay, now what does this curve tell you? This curve tells you that you cannot indefinitely operate a device without thinking about the thermal considerations. That means the thermal conductivity is going to play a key role in deciding whether you operate this device at a higher frequency or a lower frequency. And what is thermal conductivity? Thermal conductivity is this K. It is how well the heat spreads inside the device. That is what the thermal conductivity is. Okay, just like electrical conductivity, how well a material can conduct electrons. The thermal conductivity is how well a material can conduct those phonons, lattice vibrations, if it's a non-metallic system. And if you want to understand it, you can basically solve something called as heat equation, which is something like d square T by dx square plus some generation term. This is the heat diffusion equation. Just like you have the electron and hole diffusion equation, you have dN by basically the rate equation. It's the rate equation, not the diffusion equation. It's the rate equation. It's the rate equation. Just like you have for the electrons, dN by dt is dN d square n over dx square plus some generation minus recombination. It's the same rate equation, except that here instead of diffusivity or diffusion coefficient, you have something called as thermal diffusivity. And this is not conductivity. This thermal diffusivity is basically thermal conductivity divided by the density times the specific heat of the medium. This is the thermal conductivity. This is kappa. So if you want to see how this device is going to behave, you need to solve these equations. The thermal the thermal diffusion equation, the rate equation for the just like the you solved it for in case of the electrons. Okay, then you can get to know what is the distribution of the temperature throughout the device. And now what limits this performance is that at lower frequency, maybe where is that? Yeah. So at lower frequency, at this particular in this particular regime, you can see there is that this particular operation is limited by thermal management, by the thermal I should say efficiency or extraction efficiency of the device. So you cannot apply it in this regime because it will be greater than the heat which can be extracted from the system. So that's why you need to apply it in the red regime. But at the higher frequency regime, in the higher frequency regime, it is limited by the electronic response. Yeah, by the electronic response, this particular curve. Okay, so this is the high frequency regime, and there it's limited by the electronic response of the system. Okay, so yeah, this we have covered. Now let's move faster into the tunnel diodes and other diodes because then question answer session is not a big deal. There is a lot of material actually covered in the sessions. And let's now talk about this was about the frequency characteristics about the operation of this device. So let's talk about now the another device which is a tunnel diode. Tunnel diode. So the fascinating thing about tunnel diode is that you can get a negative resistance. I have not talked about negative resistance yet. Negative resistance is basically if you have the current voltage characteristics or the voltage current characteristic, let's call it V versus I. If it follows the Ohm's law, then you know that the slope of this particular thing is R. Okay, that means V equals to I times R, where this is the slope of this particular thing. And negative resistance you will be having if you have inverse of this. If you have ulta, that means this slope will be negative. That means that it's a negative resistance. Somewhere if you have a negative slope in the IV curve, it's a negative resistance. So, okay, so that negative resistance basically causes the what should I cause the generation of these oscillations in these devices. Basically, V and I are out of phase with respect to each other in all of those devices, whatever you study about transfer electron device, you study about impaired devices, you study about tunnel devices. So you will see how this will basically how this will manifest and why this manifests as a negative resistance, the how the IV curve behaves. Okay, and now we're talking about the tunnel diode. The tunnel diode basically can give the negative resistance even let's call it in DC conditions. If you apply the DC voltage, the impact diode is mostly used for small signal AC getting converted to microwave frequencies. But tunnel diodes can also be used for for I should say negative DC voltage, or not negative DC voltage, DC voltage where it can give negative resistance. Okay, let's quickly dive into what is a tunnel diode. The tunnel diode is just like a normal diode, just like a PN junction, except that these two regions are highly doped, very highly doped. So what happens is that you see that whenever they are highly doped, the depletion region will be very narrow. The depletion region will be very narrow. Rather, it's very, I should say, negligible. But because of the very high doping, there's a huge bending. What it does is that if you have N on this side and if you have P on this side, this is P, this is N. Whenever the doping is higher, that means the Fermi level almost gets into the conduction band. It's like a degenerate. It's just like a metal. Okay, the Fermi level goes above the conduction band. Similarly, the Fermi level on the P side goes above the valence band. Okay, or in other words, it can be the Fermi level can be here or here. That also means that they are very, I should say, highly doped materials. Let's consider a degenerate case where the Fermi level penetrates into the conduction band itself. Okay, so when this scenario happens, these particular bands bend like this. They bend like this, and this is at equilibrium. At equilibrium. And what happens is that you have a flat Fermi level in equilibrium, and you see the Fermi level is already above the bands in the equilibrium itself. That means that means there's a huge population of electrons here. There's a huge population of holes here. Okay, because they are already the Fermi levels are already above the conduction band and the below the valence band in the p type. Now what happens? And this particular region, this is very narrow because they both are highly doped. So depletion region is negligible. Okay. Now maybe I have exaggerated the bending as well as the width of the depletion region. Otherwise, it's very steep as well as narrow. But just to show it here in a bigger picture. So what happens now? Now what happens is that because this region is narrow, this is very narrow. Whatever the electrons are present here on this side, they are just like plane waves. They are just like plane waves, just like this. Free electron, free electrons. Free electrons behave like a plane wave. Some e to the power minus I kx minus omega t. Okay, the electrons here, they move like this, just like a plane wave. But when they encounter this particular barrier, which is the depletion region, the thin barrier, they tunnel through it, exponentially decay and appear on the other side. This is called as quantum tunneling or quantum mechanical tunneling. It's the similar process which happens if you have a potential barrier. Let's call it this as V naught. Let's call this as V0. Let's call this V naught. If this is some potential V naught, and if you have an energy electron, free electron moving here, this is free electron. By the way, this is the solution of Schrodinger equation to a free electron, which is not inside of some potential. Okay, so once the electron is oscillating here, it's a kind of a free plane wave. It hits this barrier and it starts to decay exponentially and then appear on the other side. That is what quantum tunneling is basically. But for it to appear on the other side, there should be states, energy states, energy states. Okay, it cannot just go on there and stay there. That's why if you and this particular thing is the width of this barrier. Let's call it L. That's why if you increase L, if you increase the width of the barrier, if you have now a barrier like this, if you increase this, now this is the length of the barrier, the potential remains the same. If you have electron coming in like a plane wave, it does not tunnel. Okay, it does not appear on the other side because this particular barrier length is so huge that it does not tunnel. It's a weird phenomena. It is just like electron has a sense that when it hits this particular wall, particular potential barrier, it just knows that this particular barrier has such a huge width that I'm not going to tunnel. It does not appear on the other side. Okay, it's a very weird phenomena, and people even in fact don't know why this particular thing happens. Okay, that means this particular it starts to decay, and you don't see any, you don't see any electron wave function on the other side. Basically, this is the wave function of electron as a plane wave. Okay, so that is the similar phenomena which happens here. If you see this particular pink curve, this is oscillatory, then this is decaying, it appears on the other side. Why it appears on the other side? Because there are empty states here, holes, empty states, which are the holes, which are the holes. So electron can just go into there and recombine there. Now what it does a very intriguing thing in this particular device. What it does is that it has a certain characteristic IV curve which looks something like this, which is a weird curve. So you have a region of negative resistance in this particular area. Just a second. Why is this disturbing? So this particular thing is a negative resistance. These particular curves are normal positive resistances, which you expect. But why does this particular thing happen? It is because in this particular region there is tunneling happening. Tunneling happens. So once the tunneling happens, it increases the current. Okay. Now what happens if you go on increasing let's say if you now bias the diode, because you have to bias this particular system. When you bias this particular diode, you have to forward bias it. You have to forward bias it. P plus, N plus. You know the forward bias reduces this particular barrier. If the barrier initially was like this, now you forward bias it, the barrier is going to look like this. Okay. Now what happens? The Fermi level initially was like this. This is the Fermi level. The Fermi level, when you bias it positive here, when you bias it negative, this side goes down, this side goes up, because negative is on the N side. So it increases the electrostatic potential energy of electrons. So this side went up, this side went down. That means the Fermi level here is like this, the Fermi level is like here. Okay, now there is a separation between those Fermi levels. And what it does, now if you have electrons here, if you have holes here, you see electron, if it wants to tunnel, it won't see any states present here because there is no state in the band gap. Here it was able to see the states because those states were exactly at same energy level as compared to that of the electron, which were the vacant states. Now in this particular system, if electron wants to tunnel, it won't tunnel because there is no state present in the band gap. Band gap is, that's why it's band gap. It's a forbidden gap. There is no energy level for the electron to stay. There can be defects. We are not assuming defects here. Okay, electron cannot tunnel. So even so, what happens is that reduces the current when you forward bias this particular system, and when you particularly reach this particular value of the what should I call current, and you see this particular fall as a negative resistance, which is negative differential resistance, because the electrons are not able to tunnel, so it reduces the current, which is weird. And then you might think, how does this particular curve now come up? This particular curve. Now, as you increase the forward bias more, you are creating a phenomena like this. You are still reducing the banding. This is the Fermi level of electrons, the Fermi level of holes. Now, a normal diffusion can happen. Now, the electrons can just diffuse here, holes can just diffuse here. Use just the normal p-n junction process. Okay, because there is a electron population here, which looks like something like this. This is the electron population, where this particular axis is n of E and this is E. Similarly, for the holes, there's a distribution of holes which looks something like this. These are hole distribution. But this is n of, let's call it P of E. This is E. Okay, so these electrons are going to diffuse now because they are high energy carriers. These holes are going to diffuse now. How does this come up? I've discussed in the previous maybe session of the fundamental semiconductor fundamental course. This is basically N of E, which is the product of density of states times the Fermi function. So the density of states in 3D is a function of square root of energy. The Fermi function is a 1 over 1 plus e to the power some energy divided by kT. And if you plot them both, you have this some value let's say EC, its exponent, its varies as a square root of energy. And then you have a Fermi function at some non-zero temperature, which looks like this. This is f of E. And the red is G of E, which is the density of states. Density of states is how many states are available per unit energy per unit volume. Okay, so density of states is energy per unit, not energy, number of states per unit energy per unit volume. So that's why the density of states has the unit of, it has a unit of number per electron volt per centimeter cube. Okay, so it's just like how many seats are available for electron to stay. A Fermi function is what is the probability of occupying those seats. Now you see that there is an intersection of this curve which looks something like this. This is n of e. This is n of e. That's what I have drawn here. There's a distribution of these electrons on this side, these like holes on this side. So now they're diffused by normal process and they increase the current. That is what is basically shown in this third region. So that is the operation of the tunnel diode. And now what it does is that this particular negative resistance, it is beneficial again for creating oscillations inside the system. And again, only a single device cannot sustain the oscillations. It has to be put in a resonator circuit in order to sustain the oscillations. That's why these particular things are also placed with the resonator circuit. A tunnel diode with certain LCR circuit, a certain, with certain resonant frequency, okay, which will be matched with the oscillation frequency of these devices. All right. So then there are a few things about, let's leave this. No, this won't be able to cover right now. Okay, now what about the gun diode? Okay, what about the gun diode? Let me briefly talk about gun diode, then we will start with the problems because we are overshooting the time. Briefly talk about the gun diode. The gun diode is a similar, I should say, phenomena. We first check the charge. Actually. So the gun diode is a similar type of structure. I know I shouldn't say structure. I should say the characteristics. It has also the similar characteristic. You have something like this. The IV characteristics look something like this, where this is a negative differential resistance region, this particular region. But the reason why this particular thing happens here is different. It's totally different. And this particular gun diode, it's a junctionless device. It's a junctionless device. It is weird. It's not just like you have two materials, two different materials, you combine them and you get a you get a diode or you get a device. No, it's just like a single bulk material, which is weird because that gives you the oscillation and it still has a name of diode. I think Gunn was the name of a person who discovered it, something called as Gunn effect. So what happens here in the Gunn diode? Is it the last part of it? Okay. Yeah. So what happens in the GaN diode basically is that a similar kind of curve is basically obtained, but it has a certain different reason. What is the reason? Let's say you have a material. You what you do is, so you from the basic, you solve the Schrodinger equation, you get the EK diagram, dispersion diagram with respect to the electron wave vector. Okay. So it looks something like this. Let's say this is conduction band. Let me draw it like this, like this, certain bands here, maybe some more bands. So this is the dispersion curve. Let's call this dispersion curve. This is the first Brillouin zone. First Brillouin zone. Basic device physics. So these are certain energy levels. I think is it lagging? Where does it go? Okay. Okay, yeah, it's fine. So this is the first Brillouin zone. So these are different energy levels of the electron with respect to the direction of the electron. K basically represents the direction or even the momentum of the electron because h bar k is the momentum of the electron. So in different directions, electrons move inside a crystal and it has different energy levels, acceptable energy values. So basically, in a layman sense, what this EK tells you, if you have a material with atoms, let's note as positive atoms. if you somehow shine the electron, if you somehow irradiate it with electrons, let's irradiate it with electrons or through the electrons at this particular system from all the sides. Now, because electrons are waves, what happens? Waves interfere. If I have a wave like this is one electron wave. If I have another electron wave like this, another electron wave like this, all of the electron waves, because there is certain periodic arrangement of atoms inside this crystal, the electron waves will interfere. Because of that interference pattern, there will be certain higher intensities and lower intensities. Just like you have a double slit experiment. In a double slit experiment, if you throw the electrons, you have a certain distribution of electrons. Okay, it is a similar thing. This is because of interference. The interference of electron waves happens inside the crystal. That gives rise to interference effect. That gives rise to this kind of a certain allowed energy values, which are these allowed energy values, where you have a energy maximum energy level present, or the maximum allowed value, and certain unallowed values. These are unallowed values in the Young's double slit experiment you might be knowing about. That is a similar phenomena which happens with electrons. Whenever you have an electron, so many electrons in a crystal, it creates interference of the waves that gives rise to certain acceptable values and unacceptable values. Certain values which are defined, accepted energy values, certain values which are not accepted. The energy values which are acceptable, that is represented by these curves. E versus K. K is wave vector. If you have electron going in this direction, that is kx, this is ky, this is kz. That's the similar thing. You show a single k because we don't want to confuse you. Otherwise, it's kx, ky, kz moving in different directions in the crystal. So these green highlighted curve is the acceptable values of the energies. And this region is the forbidden energy region. Electron cannot have these energy just because of the waves are interfering in such a way that there is no acceptable energy value in the system. That is why this EK relation depends particularly upon how the atoms are arranged inside the system. Okay, so just a basic, maybe you might not be knowing why this EK diagram arises in the system. Okay, so you have this EK diagram. Now, what happens is that when you solve the Schrodinger equation and other things, you get something called as effective mass, which is basically given as h bar square dou square E over dou k square. This is something called as effective mass. Effective mass is the mass with which the electrons travel in these bands, okay, considering all of the quantum mechanical effects. All of the quantum mechanics gets embedded in this effective mass because there is h bar square. Whenever you see h bar, you should inherently assume that it's something related to quantum because it's a Planck's constant. Okay, and what this effective mass tells you is that it is inversely proportional to something called as d square e by dk square. Mathematically, the second derivative of any function is actually the curvature of that function. Okay, so just like this is having higher curvature, this is having higher curvature, so this is having lower effective mass. This is having lower curvature, so this will be having higher effective mass. Similarly, okay, so effective mass depends upon the curvature of these bands, how deep, how curved they are, what is the spread of that curve. Okay, now what happens if there is an electron in this particular band, and if you apply a very high and under the very high electric field, something like critical electric field, very high electric field, electrons may go out in the other band to here. Now you see that you have a different effective masses of both of these electrons. Okay, the effective mass here is more. That means the mobility reduces, the current reduces. Okay, because effective mass is inversely proportional to the curvature. Less the curvature, more the effective mass. Okay, it's the effective mass is just like, I should say, taking all of the forces of the atoms all together, applying on the electron, and considering all of the contributions, whatever is happening with the electron, considering all of the contributions, you have a certain entity which is represented as effective mass. Okay, and here the effective mass is lower, mobility is higher, current is higher. That means when the electron goes from this region to this region, you see a reduce in the current. That is what this negative differential resistance comes in. Now, initially, when the electron was in this band, for very smaller electric fields, smaller, smaller electric fields. Oh, this is maybe this is V, no, not. This is I versus V. This V is basically electric field. Whatever you apply, that's the voltage. If you see for smaller voltage, this is still a linear fashion, just like a diode. Why? Because for smaller electric fields, electron will be electron will be mostly in this region, mostly in this something called as gamma point, gamma valley. It's called as gamma valley, and this has given some other name. Maybe I think it's an L valley, or I guess in different crystals it has some different name, maybe X valley or something. These are different symmetry points in a crystal. Okay, if you have a let's say a hexagonal, if you have let's say a hexagonal gallium nitride crystal, maybe something like this. This is a hexagonal crystal, something like this. And if you consider this point as gamma, if you go in this direction, this is X. If you go in this direction, this is maybe M. You go in this direction, you go in this direction. These are certain different symmetry points on the crystal. Okay, that's what the EK diagram is drawn with respect to. Now, for the smaller fields, the electron moves just in this band. Okay, and electron, how does the electron move in a band? Electron, whenever we apply the electric field, it gains the energy, it goes up in the band. And then here it scatters back, goes to here, then it moves here, then it again goes here. It kind of moves in this band altogether. What causes the scattering? There are other impurities in the atoms, there are lattice vibrations and other things that scatters the electron in this particular band. Now, if you apply a very high electric field, that means high voltage, what will happen? That this electron will go higher, and now something will come up, something maybe let's say phonon. Phonon is like a lattice vibration, and it's like a quantum mechanical particle. It can interact with the electron. Okay, it can just move the electron to this particular value. Okay, it can cause a change in the electron's wave vector, change in the electron's k, because here the electron was having some one k1 value. Here the electron is having some k2 value. So there is change from k1 to k2. That means there is a momentum change in the electron as well. And that momentum change is brought about by some other quantity in order to conserve the momentum. You cannot change the momentum of a certain object without any external influence. You have to have a third particle. That is why it's a interaction with the another particle which may be assisted by the phonon. So it's a phonon assisted process. Okay, so that electron comes here, it sets here. Now it moves in here in this valley. It continues to move. So you see that whenever the electron moves, whenever at the very high electric field, the electron moves into this particular valley, and the effective mass goes on increasing. The mobility reduces, the current reduces, and you see a drop in the current. And at very high critical fields, in this region now, in this region, now what is going to happen? This electron now can go still high. There are more bands above this. There are more bands. This is not the on these are not the only bands. You might have some more bands like this. So there are it's a full EK curve. There are so many bands available in the higher energy states. So what happens is that those electrons can excite to other bands, or even rather come down in this particular band and go on increasing the current again. Okay, instead of reducing it. And again, because the effective mass is changing. So that is the general operation of the gun diode. Okay, I think I've gone too much into the details. What is the other thing? And now the other thing about the gun diode is something called as domain formation. That's the final thing I will discuss maybe briefly because that is important. So if you have this gun diode now, what happens is that let me just scroll this. Not here. Just wait a minute. These things. Okay, so if you have a gun diode, then there is something called as domain formed inside this particular device. Again, that results in the because of kind of what should I say accumulation of charges because the mobility has changed. So now certain electrons will move faster, certain electrons will move slower. Okay, that is controlled by the mobility. And now there you will have some electrons here accumulating, other electrons moving forward, certain electrons accumulating here, and you have certain region of domain formed. Okay, and this domain can basically travel through this device. Okay, and this domain basically gives rise to something called as pulsing mechanism of the current inside this device. And it's the generation of this particular domain inside these gun devices that happens because of the physics I explained before. Definitely this thing. And but it's the motion of this domain altogether. How fast this domain can move and can be collected and reappear on this side again. How fast this process can happen, that determines basically the frequency of operation of these devices. Whether it will be a low frequency, whether it will be produced in high frequency, whether extremely high frequency can be produced. It depends upon the domain motion. That is the overall concept. What happens? There are other modes of the operation of gun diode. That's not necessarily right here because professor has already covered that both those particular things in the lecture. And now let's move on to the questions. Okay, I think the question should be the cakewalk now. Which device does not make use of a semiconductor junction? Yeah, that is the thing what we right now discussed. This is the gun diode. It's just like a bulk material type phenomena, bulk material. Just like it was, I think, observed in gallium arsenide, because gallium arsenide has these valleys in the EK diagram. These are called satellite valleys, by the way. Satellite valleys. This is one valley. This is another valley. So the electron going from this valley to this valley. So these are called satellite valleys. And it's very, I should say, there is a whole subject basically dedicated to the study of these valleys. There is something called as valleytronics. Okay, it's very interesting. Just like electronics, in electronics we deal with the electrons mostly here in this band when it moves in this parabola and at this bottom end of the parabola. That's what we mostly do in electronics. But if you talk about valleytronics mostly deals with how electrons move from one valley to another valley, what happens to the processes, and it's a purely quantum mechanical subject. Okay, so there are different tronicses. There is valleytronics. There is something called as spintronics. There is electronics. Obviously, you know. There is maybe what else is there? Twistronics. Twistronics. These are certain tronics which are these are particularly in development right now. Valleytronics, spintronics, twistronics. Spintronics has been around for a certain time. Spintronics basically uh, considers the spin of the electron to be as a carrier of the current, not the electronic charge, but the spin. It's a very what should I call? It's a very interesting as well as weird thing, but it has not been realized completely now. It's a very hot research topic even now, but the work was started quite almost 2 3 decades before. Valleytronics again, twistronics mostly is like if you twist certain materials, just like a graphene, if you twist that material, it results in the flow of the current. Maybe it's related to the piezoelectric effect, but it's not a directly piezoelectric effect because here you can twist the entire molecule altogether. It's related to the molecular electronics. Okay, let's not talk about that. Let's move to the next question. The thermal limit for the output power at lower frequencies in impact diodes can be bypassed by. So we saw that the power versus the frequency curve looks something like this and looks something like this. This is 1 over f squared. This red one falls as 1 over f, which comes because of the thermal issues or thermal conductivity. Okay, thermal conductivity, how well you can extract the heat from the system. So it can be bypassed by, yeah, one way of bypassing it, you can pulse the AC signal. Another is maybe uh, you can change the doping of the avalanche region. Okay, that can also be done. But one of the important perspectives is pulsing the AC signal. What can pulsing do? Basically, pulsing, if you pulse the AC signal, it will give enough time for the heat to get extracted. Okay, in the impact diodes. And what it can do is that it can give you better, I should say, thermal limit or thermal or output power at lower frequencies. Okay, so but this the time period of these pulses should be greater than the thermal time constant. The thermal time constant. It is the time in which the at least if this is temperature, if this is temperature, this is time, the temperature will fall like this. So it is the time at which the temperature falls to 1 by E of its value. So if the time period is greater than that, then the heat will be extracted efficiently, and you can have a much better, I should say, thermal extraction as well as power generation efficiency of the device. Okay, so that is the single that is the correct response for this. Okay, and pulsing mechanism is definitely useful in these microwaves. If if you have a continuous wave operation, you have a microwave output coming like this. If you have a pulsing operation, you have a microwave output coming like this. These are the oscillations. These are the oscillations. This is certain on time. This is certain off time. Okay, and these are very I should say quite a lot of applications in certain microwave devices where you need pulsing. I guess in communication they may be used certain communication techniques, or there are, let's say, certain modulation techniques. You can have the modulation technique is different definitely, but you can have these pulses just like you have a laser as a continuous wave as well as pulsed wave. That is the similar phenomena. And here you have something called as duty cycle, which is basically the T on divided by T on plus T off. And this is basically T on divided by total time period. This is the total time period of single this cycle. This is a single cycle. So this is the duty cycle. Duty cycle means how much time it remains on compared to the total time. Okay. So that is the correct answer of this question. So which carriers contribute to the current in the impact diode? So this is particularly N plus P I P plus. So in this particular system, holes contribute mostly to the current. If it would have been P plus N I N plus, then mostly the electrons would contribute to the current. Okay, just because of the band diagram which was shown, there's mostly holes drifting through the intrinsic region. So the holes is the correct answer of this question. Now the avalanche breakdown is prevented by, definitely avalanche breakdown can be prevented if you make this is particularly in impact diodes. You can prevent the avalanche breakdown by making this P region thin that we have talked about. If you make this thin, less than some critical length, then you cannot have the impact ionization process going on. Okay, so keeping the P doped region narrow is going to do the job for you. Okay, that's the answer of this question. Moving on to other, which device creates negative resistance with DC signal? Okay, with DC signal, again, we have seen that tunnel diode creates a negative differential resistance, and it's based on quantum tunneling. Quantum tunneling. That's what I talked about. If you have energy stays here, the electron tunnels, appears on the other side of the barrier. Okay, so that when you bias this, the Fermi level goes up. Now you have the Fermi levels here. The electron can no longer tunnel, and you have a drop in the current that appears as a negative resistance inside in the IV curve. Okay. Now the another question, corner frequency in impact diode is the corner frequency we talked about. If you have a maximum power extracted versus the frequency, and if you have this as 1 by f square and this as, no, I should do that ulta. This is 1 by f square, this is 1 by f, then this particular frequency is the corner frequency, okay, at which these thermal, I should say, the curve, because of the thermal extraction efficiency and because of the electronic response, they coincide. So it's where the thermal and the electronic limits of the powers coincide. That is something called as corner frequency of the impact diodes that we have discussed in the previous slides. Now, the transit time of carriers through the drift region in an impact diode depends upon, yeah, the transit time. We also talked about it. We talked about the time with which the holes or the electrons move through this intrinsic region. What does it depend upon? The transit time is basically velocity, saturation velocity, not the velocity. The length of this region divided by saturation velocity. So it depends upon the length, it depends upon the velocity of the carrier. So these two are the answers of this question. These are quite simpler theoretical questions. Now, impact diode has a carrier saturation velocity. So, so you have Vsat given as in the impact diode as 1.5 in 10 to the power 7 centimeter per second. What should be the drift region length? So you need to compute the drift region length, this of the intrinsic region in microns, micrometers, to achieve a resonant frequency of, the resonant frequency should be 12.5 gigahertz. To achieve this frequency, what should be the length? You know that resonant frequency is uh, maybe, what was this, Vsat divided by 2L. Talked about it, how this comes up. Okay, now you have everything given. You can write L to be equivalent to Vsat divided by F resonant into 2. What is Vsat? It is 1.5 into 10 to the power 7. You need to convert centimeters into meters so that everything is in SI units, into 10 to the power minus 2 meter per second divided by, this is 12.5 into 10 to the power 9 gigahertz into 2. So you get L to be approximately 6 micrometers. I've solved it, but you get approximately 6 micrometers. Okay, still just cross verify it. So that is the length of this particular region which you should be having in order to achieve this particular frequency of 12 gigahertz, 12.5 gigahertz. Okay, similar concept of resonance, back and forth thing. Whatever happens in a, if you have a particle going back and forth, a string, LCR circuit, that is the same thing. The impact diode produces an output power of this much with an efficiency of 30%. The input power is okay. Now this is an important factor. This is how the power is mostly measured in microwave or any other high frequency systems. This is something called as decibels per milliwatt. Decibel per milliwatt. Basically, it's the decibel system, but it's something like 10 log 10 P divided by some 1 milliwatt. This is the reference power. Reference power. So it is the whenever you hear the word about decibel per milliwatt, it's always reference with respect to some milliwatt. On the other hand, if you have only decibel is used to compare two values of the power or the voltage. If you have two voltage V1 and V2 or powers P1 and P2, if you want to compare those two values in decibels, you can compare them by writing 10 log maybe to the base 10 P2 divided by P1. Or you can write them in terms of voltage as 20 log of 10 V2 divided by V1, because power is V square divided by R. Okay, so the square will come in front and it will get multiplied to 10 and you get 20. That means that's why if you have, let's say, if you double the power, if you go from P2 to P1, if you have P2 to be equal to 2 times P1, okay, that means in decibels, 10 log to the base 10, 2 times P1 divided by P1, this will give you 3. That's why whenever you have a 3 dB change in the signal, let's say you have a signal and it changes like this. Let's say you have maybe minus 10, minus 7, this is dB scale, this is frequency. If a signal is going like this from minus 10 dB to minus 7 dB, there's a 3 dB change here. That means from going from here to here, the power of the signal has almost doubled. If the power was here 100 milliwatts, the power here is 200 milliwatts. That is the notion of this decibel scale. Okay, but now here you have decibel per milliwatt. So what happens in decibel per milliwatt? What is given? Yeah. So output power is given. Output power is given as 16.9 decibel per milliwatt. So the decibel per milliwatt, if you know, you can convert it into, let's say, milliwatt as 10 to the power 10, 10 to the power 16.9. Oh, let me write it in logarithmic form, not directly. So if you have dBm, you can write it as 10 log 10 P divided by some milliwatt reference power. But since it's already referenced to milliwatt, you can write it as 10 raised to power dBm given divided by, what am I doing? Okay, this will go here. Uh, and yeah, this will be divided by 10. This will be divided by 10. So this 10 comes because of the log factor. Yeah. So this is power in milliwatt. So this is power in milliwatt. Okay. So now you have 10 to the power in dBm. It is how much? How much is given? 16.9 divided by 10. So you get power in milliwatt. This is the power in milliwatt. Now what you need to compute is the input power. Efficiency is output power divided by input power. So you have input power to be output power divided by efficiency, which is 10 to the power 16.9 over 10 divided by, how much is the efficiency? 0.3, I think. 0.3. 30% means 0.3 efficient, 0.3 in terms of the values, not the percentage. Okay, when you solve this, you get approximately 163.7 milliwatts of power. I think it has to be, yeah, it has to be in milliwatts. You solve this, you get the power to be equivalent to 163.7 milliwatts input power. Okay, so don't get confused between the units because mostly people will try to trap you using these decibels, decibel milliwatt. But if you know the conversion clearly from decibel to milliwatt, from decibel per milliwatt to milliwatt, and from decibel to directly convert the values to compare the two values, you can understand what is going on with the signals. Mostly because microwave signals are used, they are mostly denoted in either decibels if you compare two signals, and if you are just seeing one of the signal, then it has to be referenced with certain values. Just like let me give you an example. Just like if you have a what should I say? If you have intensity, if you have intensity of light, you can write that in terms of decibel as 10 logarithmic of I divided by some I naught, where this I naught is the reference intensity. This is some reference intensity. And mostly it's of the order of 10 to the power minus 12 to maybe 10 to the power minus 14 watt per centimeter square. This is, I'm talking about light, electromagnetic light, light wave, not the voltages. But this is always some reference. Similarly, if you talk about in, let's say, acoustics, if you have an acoustic wave, sound wave, there you call something called a sound pressure level in decibels. In decibel per milliwatt, you write basically. This is also decibel per milliwatt. You write sound pressure level as 20 logarithmic of some pressure divided by some reference value. And in there, the reference value is some 2 into 10 to the power minus 6 or 2 10 to the power minus 6. These are certain reference values with which these measurements are mostly done. Okay, and they are, I should say, they come from the standard measurement techniques that have been already established. So what is the particular reference value with which you need to compute it? These particular reference values. Similarly, these particular reference values of the pressure, whether you are doing the sound measurement of acoustic waves in air or in water or in solid or in liquid, it varies for all of those mediums. Similarly, for this reference intensity value, it varies for different cases. Okay, so that is the notion of this decibel per milliwatt concept. Now, no, we don't need to add the page. The operation of the tunnel diode is heavily dependent upon. Okay, tunnel diode. What does the operation depend upon? Doping? Yeah, definitely. Uh, Maybe the band gap. I think mostly the doping is definitely going to be the key factor, because if you have P plus, N plus, if you change the doping, you are altogether going to change the scenario. There'll be no tunneling, there'll be no impact ionization. And that's going to have the significant impact on the working of tunnel diode. Okay. Gun diodes can be fabricated using, okay, gun diodes can be fabricated using, okay, why, first of all, silicon, gallium arsenide, indium phosphide, germanium. What is common in all of these three is that this one, and this one, they have satellite bands, satellite valleys present in the band structure. That means this type of band structure, they have these satellite valleys available where the electron can go. But if you talk about germanium, it doesn't have a satellite band. Satellite valley. Okay. The silicon also has satellite valleys. I think that looks something like this. The silicon is a indirect band gap material, so the EK will look something like this. This will be the valence band. This will be the conduction band. This is the band gap of silicon 1.2 electron volt. So when electron has to go to the higher states, it goes like this. It not exactly goes like this. It actually goes. It's again. It goes above. Then a phonon comes in. Phonon comes in, and it takes the electron from here to here and goes in the conduction band. It's an indirect transition. Okay. But for the materials like gallium arsenide, indium phosphide, they are direct band gap materials. They have a direct same K vector. Uh, they have the bottom of the conduction band and top of the valence band at same K vector, K point. This is K. So the electron goes from here to here exactly like this without changing K. But in case of the silicon, it has to change the K. That means there is a momentum change, and how you can change the momentum, you have to involve the third particle, that is the phonon. Any other third particle can work, but mostly the phonon assisted operation. This is the phonon assisted operation. It's just like electron going high, a phonon coming in, which is h bar omega q, is the energy of the phonon. So that hits the electron goes here, and this is the something called as this is basically something called as, maybe you might have seen about Feynman diagrams. That is what Feynman diagram is about. It tells us about when an electron goes here, it is hit by a phonon, what is going to hit the electron, and those space-time diagrams, maybe you might have seen somewhere in the, maybe somewhere read about. Those Feynman diagrams are mostly applicable how the electrons behave in the space-time when it's interacting with the other particles or quasi-particles. Phonon, for example, this phonon is a quasi-particle. It's not a particle exactly, but it's like a, what should I call? Uh, some quantum version of a, discretized version of a acoustic wave. Okay, that is the phonon. All right, I think we are done for today's session. I've again overshooted for this this session. What is DBC unit used? What is DBC? What is DBC? Okay, it's DBM. It's not DBC. I have told it in this particular that DBM is used if you have if you have let's say a certain milliwatt power range scale, and if you want to, let's say, uh, if you want to, what should I call, what should I say in the simplest language, if you want to measure that particular power level with respect to certain reference power level, which is in milliwatts, again this is all in milliwatts, then you just denote it in a logarithmic scale, a log scale, which is denoted as decibel per milliwatt scale. That's it. Okay, it's easier to denote these signals because you don't have to deal with the numbers so much. That's why I showed you here. If you have if you have you see what happens in this scale, in this, let's say, dB scale. If you have a change in 3 dB, you have a double power. You have almost double the power. Now, in order to show that power in a linear scale, which was not log scale, you had to show so many number of points here. going from 100 milliwatts to 200 milliwatts. But for the dB scale, you have to show few of the points because it's a log scale. Okay, it makes the calculation also again easier. You can do all of the calculations in milliwatts, no problem. But this just makes it conventional. It makes it convenient for us. Okay, in order to have these scales, it makes us easier to understand what is happening to the signal, what is happening to the amplitude of the power. Okay, most of the time when you have the experimentally when you what you do when you have the when you measure any signal, some oscillating signal, you do its FFT, the fast Fourier transform, the Fourier transform of this signal. You have certain peaks in the frequency spectrum. This is frequency, the same gigahertz. And this unit you denote it as either decibels or you denote it as decibel per milliwatt. This is the most fundamental thing that is mostly denoted as. And most of the time, if you and it's easier here to look work with decibel per milliwatt because let's say this level here is minus 90 decibel per milliwatt, and let's say this level here is maybe what should I say minus 96. Okay, so you see that there is a almost 6 dB change in the power 6 dBm change in the power level. So you can accordingly trace back that how much your power has increased, whether it has doubled, whether it has tripled. Okay, so the scale definitely goes on, I should say, it becomes convenient for us to use this scale whenever we measure the signals. Otherwise, if you have the feasibility, you can use the milliwatt scale. No issues. There is no issue at all. Okay. Oh, and it's dBm, not dBc. Okay, I think, do you have any other questions? Because we are running out of time already. Maybe I should stop the lecture video. Maybe I should stop the recording because it will be a large session. And